Hi, good afternoon, and thank you for the opportunity to speak here today. So my name is Archana Venkataraman. I'm an associate professor in electrical and computer engineering on the Charles River campus. So today I'm just going to provide a brief snapshot of my lab and highlight a couple of projects that we're doing at the intersection of AI and neurosurgery. So just as a broad overview, my lab exists at the intersection of biomedical data, AI, and clinical neuroscience. So what we do is we develop new computational models and algorithms to try and harness the information in a variety of biomedical data sets to provide either better understanding or treatment options for neurological and psychiatric disorders. We work across what I call the application, the sort of translational spectrum, from addressing foundational and computational neuroscience questions to more translational, immediate translational applications of biomedical signal and imaging data to exploratory predictive analytics for healthcare. And all the while, we're addressing some key challenges in the space of neuroscience and neurosurgery, which are small data sets, extreme patient heterogeneity, interpretability, and just poor data quality control. So the two projects I want to highlight here today both involve identifying targets in the brain that are useful for neurosurgery in two different contexts. So the first context, which I'm showing on the left of the screen, is localizing eloquent cortex regions for preoperative planning. So if a patient requires a neurosurgery, so for example, removing a tumor, then it's really crucial for the neurosurgeon and the entire clinical team to identify areas of the brain that we don't want to damage, known as eloquent cortex. So by identifying eloquent cortex, we can find a safe resection pathway to actually perform the surgery. So eloquent cortex tends to be associated with the motor and language areas of the brain. Now, on the other side, the second projects I'll highlight is the work we've done on epilepsy. So for epileptic patients who don't respond to drugs, our goal is to really determine where in the brain the seizure is originating so that potentially that area can be removed and the patient can become seizure-free. So with those two, so in both cases, we've developed deep learning or AI models to really tackle this challenge. So for the eloquent cortex localization model, what we've done is we've incorporated dynamic information from a modality known as resting state fMRI. So it allows you to track network patterns and organization in the brain. And this model that we've developed combines both spatial information and temporal information to provide maps in the brain of where key motor and language regions of the brain are. Really crucially, it actually can operate with missing data during training, so we don't need a complete data set for all patients. If some patients are just scanned for language paradigms and some patients are scanned for motor, we can handle that as well. And then we've evaluated on real-world clinical data for this resting state fMRI, and we showed that our model is actually able to localize these eloquent cortex regions. In fact, it's able to find bilateral patterns even when it's never seen that before. So for epilepsy, we're doing a very similar exploration with this resting state fMRI. So once again, we're looking at network organization of the brain, and the idea is that the communication of the brain is disrupted by seizures. And so can we actually find that disrupted communication? And once again, we have developed a deep learning model using graph neural networks, and we folded in very strategic hypotheses and biological constraints, including the anatomical wiring of the brain, the fact that we want the seizures to be lateralized, and the fact that each subject will have different influences. We might have different scanners, et cetera, that we need to accommodate. And once again, we've evaluated this on real-world clinical data, and we're able to actually localize these seizure onsets in pediatric epilepsy cases. So both projects, I think, provide really fruitful opportunities for further collaboration and for trying to translate some of these technologies into a really challenging space of neurosurgery. Thank you.